Thanks, guys, for coming. Before we start, how many of you have already, visited talks about Apache Ignite throughout these days? So this means that for you, those are who is going to listen about Apache Ignite for the first time? Okay, no one. Okay, great. So, and this specific talk, I'm going to cover SQL capabilities of this platform and of this database. Because you might know that Apache Ignite was used as a data grid, as a caching layer on top of some relational databases or NoSQL databases. At the same time, you know that Ignite provides different computational and machine learning APIs on top of the storage it has. But at the same time, you should also know that Ignite has a pretty powerful SQL engine embedded into its architecture. And today I'm going just to show you, probably to list the main benefits and the main features of the SQL functionalities that is built into the Apache Ignite. And a couple of words about myself before we set off this conversation. My name is Dennis Magda. I'm Apache Ignite PMC chair. And at the same time, I'm taking a role of Grid Gain Director of Product Management. However, I joined Apache Ignite community and Grid Gain pretty long time ago as a software engineer. And I'm still a pretty technical guy who is able to answer on a variety of tricky technical questions you might have or you might get throughout this conversation. So be free to prepare them and ask them at the end of this talk. Well, agenda for today. I'm going to briefly list all the main capabilities that are usually found in every standard SQL database. Ignite is not an exception here. I'm going to explain how you can connect to Ignite from your applications, what are the protocols and the gateways available for you as a developer. Next, I'm going to briefly talk about data definition and data manipulation languages. What's the scope? What's kind of a specification that Ignite is based on, and other interesting things about our SQL engine. Next, as a database of the 21st century, Ignite provides more than just SQL on top of its distributed storage. You can use a variety of APIs, such as KeyValueApplies, machine learning, or for instance, you can write your application code in such a way that you can benefit from so-called collocated processing. And I'm going to give you some insights on how to exploit this collocated processing technique in practice. And finally, once we are getting closer to the end of this conversation, I want to give you some, I just want you to form some understanding on how the memory architecture of Ignite looks like and how all this SQL engine and the distributed storage are coupled together. And throughout all this conversation, I'm going to beef up my theoretical part with a variety of different samples. So we are going to run the cluster, we're going to connect to the cluster and do some different manipulations with the data we are going to push into it. Okay, SQL capabilities. We are going to skip all this standard blah, blah, blah about Apache Ignite. I do believe that you're already kind of pretty overwhelmed with all this information about this platform. So we are going to switch directly to the SQL. That's one of the slides that you might have seen before. And the main idea of this slide is that Apache Ignite as a distributed storage, as a distributed database, it consists of multiple cluster nodes that are interconnected with each other. And you can push and store all this data in these cluster nodes evenly, meaning that every cluster node will be responsible for a subset of the data you have. And the same becomes true for indexes. If you define indexes, primary indexes, secondary indexes, all the indexes will be distributed and stored close to the data that are indexed by them. And on top of this distributed storage, on top of these data sets, that you have in your cluster, you can start using Ignite as an SQL database. You can connect to Ignite by means of so-called native SQL APIs. Those are just APIs that are available for Java, .NET, or C++ developers who are lucky ones. They have special native libraries developed by Apache Ignite community for them. But at the same time, if your favorite language is different from Java or .NET, let's say, you can use JDBC or DBC as a way to talk to your cluster. For instance, you can connect from your Python application, or you connect from your favorite tool that you use for analytics, like Tableau or anything else, and you can start working with your cluster solely by means of SQL queries. Well, how do we connect to this cluster? As I said, if to start from the bottom, we do have Java, .NET, and C++ libraries. And if you connect from your Java application or .NET application, you can just start a special client node, embed this client node into your application, and this node will connect to your cluster. And then right after that, you can start writing a variety of different SQL queries. However, Ignite supports other type of APIs, REST protocol, or what's more interesting for me is JDBC and ODBC drivers. Like it's shown on this picture, you can see how you can connect from Ignite to Ignite using a standard JDBC driver connection. And here is, for instance, we are going to use one of the tools. The tool is called SQL Line Tool. It's developed by some of the folks who are part of Apache Ignite Software Foundation. And we in Apache Ignite community decided to use this SQL Line Tool as the main command line tool for SQL capabilities in Ignite. So now let's switch to the demo and to see how we can quickly connect to our Apache Ignite cluster from this tool. The tool that uses JDBC driver. First, I need to start my cluster. I'm going to start it locally, because I'm a developer, and before I deploy anything in production or on the cloud, I want to write my application on the hardware I have at hand. And here is how I start my cluster nodes. I use a special Ignite SH script, and here is I feed this configuration to the script. This configuration doesn't have anything interesting. It just includes some networking configuration parameters that allow all these two nodes to look up each other on my local networking interface and to interconnect to form a single cluster. Okay, so the first node is almost up and running. Okay, so the first node is here, and we are waiting for the second node to join the cluster. Okay, the second node is in the cluster, and now I want to connect to this cluster from my application, and I want this application to be I want to connect from using SQL Line Tool, using JDBC driver. Okay, here is I connected to the cluster using this JDBC connection. And presently, we don't have any table deployed. Our cluster is empty, right? So there is nothing to do with it, just connectivity. But let's move on and to see how we can quickly push and put all this data into our cluster. Let's see how we can make use of it. And here is we coming to the next topic. Before we can preload or push any data into our Apache Ignite database, we need to create tables, we need to define SQL schema, and we need to create indexes for sure, because we want to have queries that run quickly. And Ignite released data definition language not that long time ago. Probably a couple of months ago, Ignite community provided support for create and drop table commands. And at the same time, right after that, Apache Ignite community implemented create and drop index command. What's cool about this create and drop index commands is that now in Ignite you can define and update indexes in runtime. Before it wasn't possible. Before, if you plan to introduce a new index, you had to restart your cluster. Now you don't need to do this. Now you just can connect to your cluster that is up and running, and you, for instance, can create a new index using a standard SQL syntax. Finally, your data model objects, they for sure will evolve over the time. You will add new fields, you will remove old fields from your classes, but at the same time, you want these fields to be accessible and visible from your SQL queries. And to do this, you just need to use alter table command. That is also a standard way to update your SQL schema. Let's imagine that you added a new field to your business model object. And now, if you want to use it from SQL, first, you need to add it to your SQL schema using alter table add column command. And then if you need, you can index it. And finally, all these changes, if you enable Ignite native persistence, if you want to have the durability in your cluster, all these changes that are doing on an already running cluster when you're adding indexes, removing indexes, all these changes will be persisted, meaning that if your cluster by some reason gets restarted, you don't need to re-execute all these create, drop, index, or alter table commands. All this information will be persisted all together with your data sets and indexes. Okay, now let's take a look how we can create several tables in our Apache Ignite cluster. We are already connected to it. And here is somewhere I have some SQL script prepared for this talk. Okay, it should be somewhere over here. Yeah, this big one. No, it's better to open it in a different way. Please bear with me. Give me a second. I have it here, what I'm doing. Here it is. So here we have some standard SQL script. Basically, that's a database of all the countries and all the cities in the world with the information such as population, language, and so on and so forth. Here we have different three tables in total. Country, city, country language, and all the data we want to preload into our database. So what I'm going to do, I'm just going to run the script from my SQL line connection. To do this, I need to use a special command supported by the tool. And I need to specify the script name. Okay, the data is being preloaded. And while it's being preloaded, I want to connect to my cluster from a management console. I want to see what's going on with my cluster. I want to see how many nodes I have, how much data is preloaded into it, and I want also to execute some queries from it. Okay, let me see. Okay, I've connected to the cluster. Here is my two local nodes. And here is I have all these tables or caches. So when you execute this create table command, if you know the architecture of Ignite, we will create SQL schema tables, and also Ignite will automatically deploy caches for you. So in Ignite, caches is a data structure that stores data sets in a distributed way across a cluster of machines. And here is we have this data. The data size is tiny, but anyway, here is I just want to demonstrate you how you can create, configure your cluster, and insert data into it using standard SQL syntax. Finally, okay, the data is in the cluster. What else can we do about it? Data manipulation language. So, but actually both data definition language and data manipulation specifications, they are ANSI 99 compliant in Ignite. So everything that is listed in this specification is supported for DML, and we keep improving our data definition syntax. It's worth mentioning that all the queries like inserts, updates, and deletes, or selects that you run over your Apache Ignite cluster, they are fault tolerant and consistent. So meaning that if during a query execution, your cluster topology changes, like you add new cluster nodes or you remove the old one, your query is guarantees to return you a complete result set and consistent result set. And speaking about SQL queries, Ignite does support joins. So you can have two types of joins in Ignite. The first one is so-called collocated joins. The idea here is simple. Imagine that you have some relations between your in your business model. Like you have here is we have country, cities, and country language, and we can build a structure when all the cities belong to some country, and languages also belong to some country. It means that at the cluster level, you can store all the data, all the cities, for instance, all the cities from the United States, on the same machine where the United States record is. Like here is, if we assume that all the data is collocated, we call this process affinity collocations, then all the United States cities will be located here, and for instance, all their Brazilian cities will be located on the other nodes. And when you decide to execute a query with join, when you need to join data between cities and countries, the SQL engine will know that all the data is, like all the data between dependent tables is located fully on the nodes, and there will be no any data movement across the nodes, and we will be able to accomplish an SQL query with join in the fastest way possible. And this is what it happens here. Like when you start some query like this one with join, here is we're trying to join data stored in city and country. We will send this query right away to all the destination nodes, and that query will be executed over the data set that is available locally, and you will get your data back. But at the same time, sometimes we cannot collocate all the data. Like imagine that you have in your business application, you have cities and you have cars. There is no any relation, or like you have probably cities and departments, and you might not have any relation between those tables, but you still want to join the data stored in these tables. And here is you can use so-called non-collocated joins. The difference here is depicted in this tiny block. When a query with a distributed join is issued to these nodes, when a node starts joining data and it understands that some of the data set is missing locally, it might connect to other cluster members requesting the data to fully and consistently join the result sets. And once this is done, your client application will get a result set back. For sure, this type of joins, they are less performant than collocated ones, but what they give to you, they allow you to use, to execute, to write and develop 100% of SQL queries you need for your business needs. Because usually in my practice, in my personal experience, people are able to collocate all the data in such a way that they can query it, that 90% of queries can rely on collocated joins. And then for 10 or 5% of queries, you can use non-collocated joins. So that's what we do. And now let's take a look how we can query the data. For instance, how can I query the data from my Java application? Here is I have my simple Java application. I'm going to connect to my cluster of 2 nodes. Just to remind you, all these 2 nodes are running here in 2 different system processes. And now I'm connecting to these nodes. I'm going to get a reference to the data, to my caches. And next I want to execute three simple queries. First, I want to get the most populated country in the world, 10 most populated countries. And also I want to return the most populated cities in United States, Russia, and China. Here is I'm going to use joins. And finally, that's the simplest query you can run in every database you have. Like I'm going just to select some random record of a random city. Okay, let's start this application. And while this application is being launched, let me connect let me get back to my web console and to see, and I'll try to run the same queries from this console. For instance, here is I have the same query. I'm going to run, I want to get the most populated cities. This is what we see. China takes the first place, which is not a big surprise. Then we have India, United States. If you want to run a query with joins, we can do it directly from this web console. And here is we can see that the most populated city turns out to be Shanghai in China. Then we have Moscow in Russia and New York in the United States. And if we go back to our application, we ran the same queries from my Java application using those native APIs. You remember I was talking about the native APIs that are available for Java.NET developers, and usually these are those native APIs. You just need to connect to a cluster from your application, and then you can use special APIs like SQL Fields Query to run your SQL queries. Next, let me try to, and for sure you can update. So if you have an experience with Ignite, probably you try to update data sets using KeyValueApplies or computations. But here is I want to show you how you can do the same with standard insert, update, delete statements. Here is we have some city located in, I think is Uzbekistan. And now I want to update city's population. I want to lower down the population to 150 to 1,500. And we can see that the change was applied. Next, for sure you can delete this city if you want. And there's no surprises, any other database Ignite can do this for you using standard syntax, nothing like that. And the other thing that makes Ignite different from, let's say, conventional relational databases is that that's a fault-tolerant database. Like now, if I go ahead and destroy and kill one of these data nodes that store my data sets, I will not lose any data. Let me terminate it. Now I have only one single node running. But if I go ahead, I lost connection from my web agent. Let me try to, I know how to fix it. I need to provide a different port number. So my web console disconnected because it was connected to the port number that was running on that node that I've just killed. That happens, where is my web console, my web agent? So I need to go here, and I need to, I think that the second node is listening on this port number. Let me check it up. Okay, I've connected to the console. Okay, I could connect to my cluster node, that is the only one node that is left. Anyway, so the goal here was not to demonstrate that the fault tolerance of the web console is not supported on my local laptop. The goal was to show that now I terminated one of the cluster nodes, but I still will get a complete result set. Here is I keep executing the same query, and you can see that the data is not changed. So like, you can, let's double check that. Yeah. Or we can use some other city, Ukraine. We don't have this country code. What can we use as the country code? I don't know. Brazil? It doesn't matter. Anyway, so you can see that even after we killed one of the cluster nodes, you still have all the data set locally. And why? Why is it so? If you go back to our SQL script, here you will find some special additional parameters, such as this one, that says that I want to have a backup copy for every record that I place into my cluster. And if you recall, I had initially 2 cluster nodes, which means that each node was a primary node for some subset of the data, but at the same time, every node was stored a copy of the rest of the data set. And this is why I didn't lose any data.
So your search was local then again on the same node?
Now it was, yeah, now it was kind of, now the query was sent only to this only one node that I have.
And the join happened both of them?
No, before it happened on both nodes when I had 2, but now I had only one node and it happened only on a single node. Okay, now I want to bring back my node. Okay, let's wait while it's being studied and move on with the rest of the content I have for you. Collocated processing. So all this was about SQL. So what's good about SQL? It's a standard language that we can use to write and develop advanced queries for our applications. But at the same time, there is one pitfall, which means that when you kind of deal with big data sets and your SQL query has to return you pretty decent result set in size, then you can quickly saturate your network if you start moving result sets, big result sets over the wire. And if you want to avoid this data movement from your database, from your cluster of your machines to your applications, you can exploit so-called collocated processing. What this collocated processing stands for a way when instead of, like it's shown here, instead of sending a query like SQL query or KeyValueApplies to your database and getting back all the data back for the processing on the local machine, you can do a different thing. You can rather write a piece of code that will be sent to all the server nodes you have, to your data nodes, and this piece of code will be executed directly over the data you have. And here is, as you can see, all the processing takes place here, and finally you might get some tiny result back. For instance, this technique is widely used in different financial institutions. Let's say when you need different banks, they store deposits, and once a month at least you need to increase you need to just to apply some interest to the deposits you have. And if you would do this in a standard way, this way, you would need to preload all the deposits from your database to your client applications, update them locally, and send them back. Or you can write a simple application logic in a MapReduce fashion and send this logic to your database. And all this logic will be applied and executed over the local data sets you have here. And this is how you can avoid excessive data movement over the network. Okay, so what can we do with this in Ignite? Yeah, we can write some computation logic, MapReduce tasks, but here I want to show you a different thing. Here I want to connect to the same database I have with all the data we have using Apache Ignite KeyValueApplies. So as you know, KeyValueApplies is probably, if you know a primary ID of your database, of your key, of your record, you can just quickly connect to it and update it using that ID using KeyValueApplies. Like for instance, here is I have this application. This application connects to the same cluster that was created and populated using SQL syntax. But now what I want to do, I'm connecting from a different application to my cluster And I want to, for instance, get a record of Amsterdam. That's a primary, that's an identifier of Amsterdam. And I want to reduce city's population a bit. We decided that people moved out somewhere to some neighborhood city. And you can do this by means of key value operations, cache, put, get. At the same time, you can execute different transactions. Like here, as I want to start a distributed transactions, I decided that actually those, here is I have a primary key of Amsterdam and the primary key of Berlin. And here is what I'm trying to do. I'm starting a pessimistic repeatable read transaction. And inside of these transactions, I'm going to do a sort of immigration. So I've found out that 100,000 people moved out from Berlin to Amsterdam, and I want to update this information in transactional boundaries. And this is how I do this in Ignite with KeyValueApplies. Unfortunately, I don't know how to increase this font size, but this worked. So I could update, I could modify, and if I, let me see, so here is before it reported that Amsterdam population was around 731 to 100. But now if I go back to my SQL, I can check up that the data was updated. Yes, so it grew up to 800,000. That's good. But here it's not collocated processing, right? It's just a way how you use KeyValueApplies in Ignite. But what's about collocated processing? Here is I have the same thing. Here is I also want to update city. I want to do this migration between Berlin and Amsterdam. But here is I use so-called city entry processor. We know that I want to update a single field in my record. But to do that, with the first example, I had to read all the data back to my application, update it locally, and send it to the database. And here is I'm doing a different thing. I'm starting the same transaction, but I'm created a special entry processor. It's a piece of, it's a kind of, it's my task, it's my kind of it's my kind of calculation that can be run on specific cluster nodes. And here is what I'm saying. I want to get a record for the key I'm going to pass into my source code, and then I want to increase the population. Here is I'm going to add it, and here is I'm going to remove. Anyway, and here is you might mention that we are using special type. We are no longer using city or city key objects that were used in this application. And here is a reason for that. Because this logic will be executed on my database size. And I do not want to have classes of my business model objects on my database size where I store all the data. Because if I decide to update my business model objects, for me it will mean that I need to restart my database with all the data set. I want to avoid this. And when you need to update some data or that is stored on your data nodes, you need to use so-called binary object wrappers. It's a sort of JSON-like API. Here is, as you can see, I get my data serialized in the binary object format, and I'm just updating special fields. I'm getting values of some fields. This is how I work on the server side when I do not want to have the deserialization. Let me quickly run this example. And by the way, when this logic will be executed, it will be executed on the server side only, right? And we expect to see this output in one of my nodes that are running here. Those are my data nodes. Those are the nodes that store my data set. Okay, so here as you can see that the first logic was executed on this node. And I guess that the second one, what are you doing? It's waiting for someone. Yeah, I don't know, it was doing something, some lag. Anyway, so let's double check. Yeah, it turned out to be that both keys, Amsterdam and Berlin keys, were stored on this specific node. And these two calculations arrived here. And this is how I updated the data in the collocated processing fashion. And finally, briefly talking about their architecture, Apache Ignite memory architecture. This is how all this works, how we can use and reuse different SQL APIs and key value and processing APIs in Ignite. All the data is stored in so-called durable memory. So we have the data might be located in RAM, in the off-heap region outside of Java heap, so that you can store massive amount of data and not worry about garbage collection. Or if you need disk, the data will be located, persisted on disk for the durability. Speaking about the disk, it looks and works the same way as many other disk-based databases. Like when an update comes to your cluster node, first it's written to RAM, and then it will be immediately persisted to the write-ahead log file. Once this happens, your application will get an egg, and it will be able to proceed with the rest of the logic it has. All of the time, all these pages all this data that was updated here it's marked as a dirty data, as a dirty page, and all this dirty data will be written back to the disk in so-called partition files. We need the partition files to boost the restart of your cluster, because you know the write-ahead log file grows endlessly. And once we push all the data, all the dirty data to partition files, we can trim the write-ahead log file, remove all the changes that we already applied to partition files. Next, that's how the durable memory architecture looks internally. It's pretty kind of complex. All the RAM you have, it will be split into the special memory regions. You can configure them in size. You can say that for one region, I want to have the persistence enabled, while the second region might work with in-memory data only. So you are fine to lose the data that is stored in this region. So it's up to you. Then every region is split into segments. And every segment, if you take a look in the next picture, every segment consists of different pages. Pages like in Linux, or other Unix-based operating systems, they also have a page-based memory, and Ignite implemented the same approach. So we have data pages for your entries that you add with your insert, update, delete commands. Next, we have indexing pages. So those are for indexes. And they have some meta information that is stored in the memory. Speaking about indexes, all the access, whenever you try to select, run an SQL query, or whenever you try to execute cache get operation using KeyValueApplies, all the queries are coming to a special B+ trees. So for every index you have, we maintain a separated B+3 data structure. And this B+3 data structure stores indexes both in memory and optionally on disk if you enable the latter. And finally, speaking about how the memory is allocated for Ignite. When you start pushing the data, inserting data into the cluster, you need to get some space from somewhere. First, Ignite, if to go back here, Ignite requests memory segments from operating system. This is where Ignite starts interacting with your underlying operating system. But then, when it has a big chunk of memory taken from the operating system, you need to use it wisely or kind of frugally. So, and we have a system similar to the body system of Linux, where we have special free list data structure that tracks pages of the equal free space that is left. And for instance, when you need to insert some entry into your memory, and we know that this entry can fit into the page that has 25% space left, then we will use this space. We will use this page. And this is how Ignite is able to reduce fragmentation routines that happens continuously and endlessly over the time. And this is how you can lower down different compaction activities. So that's all about our SQL capabilities. That's all about our memory architecture. So feel free to start using Apache Ignite as a SQL engine, because to my knowledge, the Apache Ignite community keeps investing a lot of resources into the evolvement of all the SQL capabilities Ignite presently has. So thanks for attending, and I'll be happy to answer your questions, if any. If not,
So when you did the search by having each app search some database, if you didn't do the backup equals to one, there won't be duplicates. What happens?
Then you will lose a part of your data set. Like,
That's fine, but I'm in the Brazil versus US, and you search with a join,
uh-huh.
and how is it going to work? Is data going to move to the other nodes, or each one is only searching its own, and how does the join take place?
So like here is, let me show it to you.
And where is the
Yeah,
join?
I didn't show this to you. Here is I use the I collocated data. You know what the collocation is, right? Like that relationship. Yeah. Let me show you the script. Here is I have country. Country is my kind of main business entity. And then I instruct Ignite to place, here is I have affinity key. I instruct to place all the cities, let's say from Brazil or from the United States, on the node that will store a record of the United States or Brazil. This is done by this tiny configuration parameter that is passed into my create table command, affinity key. And then when I ran those queries, all the data was already, all the data, like all the cities of Brazil and all the cities of Brazil were located on a single node. And all the cities of the United States were located probably on a different node, but all together. And this way, when I executed this join, I knew that all the data is here. And the nodes, both nodes that stored the data, they did not interact with each other. If I removed this parameter, then cities, Brazil cities, might be located across different nodes. And then during the join, both nodes would be interacting with each other, shifting data needed to complete the join.
Now, in the case that you did, where each one is separate from its own cluster, right? Who did the join? Did it go back to the client?
Yeah.
Where did the join take place?
Join takes place on the server side, like here is.
Each one only has access to its own data.
Yeah, correct.
The join requires the result from the other one, from the second server, because that one has Brazil.
No, yeah, I see.
And the
Yeah.
US one has just the US and its own data.
Yeah, I got your
If
question.
you join looking somebody up in both places, then he appears in both
Mhm.
places.
Yeah, here's what happens. First, right, like you are saying, the joins will be executed locally, and every node will prepare its partial result set, right? And then this result set will be sent back to your query initiator, your client application, your SQL tool, and that tool will do the final thing. It will reduce
So
it.
the join
It will-
actually takes place on the client, not
No,
on
no.
the server nodes.
No, servers join the data, and they will send it back. And if you need to final it into
So
complete,
they cannot join it because they have their own piece.
yeah, they join their own piece, and you will get a result set. Like for instance, imagine that this node stored United States, and this node stored Brazil.
Yeah.
So they joined all the data needed for the United States, and that one for the Brazil. So there is nothing else to join between these two data sets, right? And this client application needs to do the final thing. It should take both results sets of two joins and to combine them and give back to your application. Make sense?
What happens in case of order by, and you have a numeric?
Yes, so here is, as far as I remember, in case of the order by, both servers have to stream data back to the client, and the client will do the join in this scenario, because client has to order the data.
So mean and order by, these kind of operations might be something which is more less performant than really your.
Yeah, it might be, but now, as far as I know, our SQL committers, they are doing a sort of a merge sort improvement so that you can somehow initially merge the data locally and then send different chunks to your client, to avoid all this to avoid any performance drops caused by, and extra memory consumptions caused by order by statements.
But related to this question, which is sort of similar to what I was asking, but that was a join. If you're ordering it, who's doing the ordering? Is the server node, like number one, getting the list from the second server and ordering by combining with its own and serving it? Or both sets are going back to the client and the client is responsible for
Client does the final ordering. And client, as I said, client does the final joining. But it just takes what was provided and it just combines.
that
Yeah.
makes sense?
Yeah. Uh-huh.
Because they're not really interacting amongst themselves.
Uh-huh. Any other questions? Okay, then thanks for coming. See you around.